So let's look at this problem, time bandwidth optimization. So let me explain to you what the problem is. This is so So we have a pulse. Pulse, of course, is by definition a waveform which is non-zero only over a finite duration. So the duration is, this is the duration of the pulse. As a rule, if you look at its transform, it's going to be represented all over the frequency domain. But what we mean by time bandwidth optimization is we want to be greedy. We want a pulse, but we also want the transform to look like a pulse. So that's not going to be possible. Then we want to do the best we can. So the question is it possible to, like here, remember this is clean because there is no spillover beyond a t. Is it possible to get a pulse whose transform is within a bandwidth that you are interested in? Let's say this is the band. You want all the energy to be here. So the answer is no. But then, of course, then we compromise. Then we see what is the next best thing we can do. So here is the problem. Find me a pulse which has got maximum energy within this. So all this I am going to call it as side lobes or leakage. The leakage is as minimum as possible. So it's like saying I want to have the cake and eat it too, right? You want to be finite here. You also want to be close to finite here. So what is the best pulse? Let's say. So let's look at the pulse energy. Remember, the total energy is going to be ft squared dt integral 0 to t, because this is a pulse. And anyone, I'm going to assume, it doesn't matter, I'm going to assume this is 1. That means we start with a pulse which is of normalized energy. Anyone knows how do you express this relation in the frequency domain? How will you express the energy using the Fourier transform?
1 over 2 pi integral minus infinity.
All right, that's the problem. This energy is all over the whole band, minus infinity to plus infinity. So if I want to concentrate here, I should bring up, I should look at a filter like this. So this is in the frequency domain from minus B naught to B naught. And I'm going to call this h omega squared, okay? Let's say the height is 1. Well, remember, so I'm going to start with what I want. This is what I want to maximize. Somehow I want to maximize the energy within this is what I want to maximize. What is your freedom? Anybody? What is my freedom to maximize? What am I maximizing it on? This problem, I explained to you the problem. I have nothing else. So where is my freedom here? One thing is very clear. I want it to be unit energy. I don't want it to spill beyond t. The pulse is only living from 0 to t. So where is the freedom? Anyone?
You can take a different type of FT.
So your only freedom is in its shape. So maybe this shape is better. Will have more compressed energy. So this is shape. That's the only freedom you have. Your freedom in choosing, in selecting the shape. Right? Nothing else. Energy is fixed. Duration is fixed. So I'll say the maximization need to be done on ft itself. There is nothing else. So you look at here. This energy is and bandwidth is fixed. Three things are fixed. Energy is fixed. duration t is fixed. In the frequency domain, b naught is fixed. I'm also telling you that, so actually I want it to look like this if possible. I want all the energy within a band, but that's not possible. But I want to select a shape so that whatever is outside is, idea is that these things are as minimum as possible, so that, remember, this relation is true. So if these things are minimized, things are has to be maximized here. That's the logic. So to proceed this, to get rid of this, I want to rewrite it like this. So what should you do to f omega squared? Anybody? Instead of writing it in terms of b naught, I want to write it like here, from minus infinity to plus infinity. That's where this function would help. So what should we do to that? No. If this shape is h omega squared, right now this is not equal. How do you make this equal to this? What can I do with h omega squared?
Just multiply.
All right, very good. See, you can say this is true now, right? Because this is 1, so we are just ignoring this region, which is what. See here, all it says is that whatever is this thing, I'm only going to integrate here. That's what this integral says, right? So, but that's a clever idea, but you can go back to the original shape and write it like this, right? Now, you see that, of course, if you want, you can write it as okay, so let me call this to be a of omega. Anybody remembers what is Parseval's theorem? I have minus infinity to plus infinity a omega f star omega. That can be, do you know how to translate this into time domain?
2 pi.
All right, so let me put a 2 pi here. I forgot. So 1 over 2 pi. That will take care of your 2 pi. So this is equal to what? In time domain. So let me call this inverse transform of this to be phi of t, for example. Okay. So how will you write this now in terms, anybody? And of course you know the inverse transform of this, of ft. Then? Have you heard about this? No? First time in life or no? We did this last time, right? Last week. Cannot be first time in life. What about the limits in general? Don't you remember this? I said ft dt, gt dt in time domain it is like this, or in frequency domain f omega, or either way f star omega, g omega, d omega. So limits are from minus infinity to plus infinity. But look carefully. I'm going to force it. What is the? This may be minus infinity to plus infinity, but this pulse lives only from 0 to t. So I can write this as 0 to t. And phi t, let's look at phi t. Phi t is of course the inverse transform of h omega squared and f omega. So phi t can be written as what? Anybody? Remember, this is the multiplication in frequency domain. Convolution of what? Not ht. Whatever is the inverse transform of this, let me write it like this, and f of t, right? So that's this we know the inverse transform, so we can plug it in.
There will be one more correlation.
Huh?
Phi t star.
What is the inverse transform of h omega squared? Let's just find it. It's h omega is here. So phi of tau, which is 1 over 2 pi h omega squared e raised to j omega tau, or t d omega, right? This goes from minus b naught to b naught, and this is 1, right? So this is e raised to j omega t over j omega 1 over 2 pi minus b naught. We went through all this. What is it? So the numerator is 2j sine b naught t, right? Not b. Yeah, this is t, right? Because integration is with us. So sine b naught t over b naught t. Then I have to introduce a b naught and divide by pi.
Yes. Right.
Very good. All right. So this is going to be sinc b naught t b naught over pi, right? This phi of t, right? So this is going to be sinc b naught t minus tau f tau d tau. But this goes from where to where? Anybody? What are the integrals? Convolution. Look here. F tau. F only goes from 0 to t. So this is like this. Okay, so we got phi of t. But look here. Here is the punchline. We know this. So we know now we can apply Schwarz inequality here. So this quantity is less than or equal to integral phi t squared 0 to t integral ft squared dt, right? And we get equality when? Yeah?
No, we should, for this we should have a square.
Well, you don't need a square. Look, that's a good point. Look at here. This is already positive. On a positive quantity, if I put this, it's not going to make any change, right? So of course I can put a absolute value. It doesn't matter.
We need an absolute square, right?
All right, hold on. First of all, putting an absolute value doesn't make any difference. So if I put an absolute value here, it doesn't make any. You're right. So I should put a square root here, right? But this absolute value is meaningless, right? Because it's already a positive quantity. So remember, we want to maximize this. So we want to get equality here. Anybody know? Now when will you have equality? When these two functions are proportional because of this star. So equality is when phi t is proportional to ft. But phi t is already here. So let me put everything together. So EB naught is maximized if integral 0 to t sinc b naught t minus tau f tau d tau is lambda ft, right? T from 0 to t. And there's a constant here which I forgot, which is b naught over pi. So this is the answer. Remember, we have been looking for ft. So ft should satisfy that linear equation. We can do a little. So these are very classic problems. The solution is known as prolate spheroidal functions. So this is your phi t now. So phi t should be proportional to ft. So let me make a small change in variable. Let me call b naught t to be x, b naught tau to be y. So from here, so this equation now reads look at here. So this is b naught over pi integral 0 to. So let's see when the variable is tau. When tau equal to 0, the lower limit is 0, pi is 0. When tau is t, this is b naught to t, right? And here you have sinc of y minus x, x minus y. And here you have f of y is a tau. Tau is y over b naught. And d tau is dy over b naught. So this b naught will cancel with this, right? And on the other side, you have lambda multiplied by f of t, which is x over b naught. Okay. And let me absorb this pi here. So I have a new equation which reads so I'm going to call this so notice that whatever is the f function, it's in the so I can call this to be an f tilde, right, in terms of y, right? So I can rewrite, remember this says y and x have no meaning, it's just y is certainly a dummy variable. So if you agree, then I can rewrite it like this, right? Except why I put the tilde is I am not referring to the original function, but the time scaled by b naught, right? T over b naught is what I am calling f tilde. And so this t now goes from 0 to, remember this, so here this is also from 0 to b naught t, right? Because look here, when t goes from 0 to t, when t is 0, x is 0. When t is t, x goes to b naught t. So this is your x, right? B naught t. Remember here, I had x here. I decided to replace x by t because x, it doesn't matter. So ultimately, you just look at this equation. So the interesting thing is, only the time bandwidth to product matters. So if you know the pulse width, and if you say I'm interested in a certain bandwidth, look at here. You can solve this equation. This equation, if you discretize it, is of this form. Anybody is familiar with an equation of this form? Ax equal to lambda x. Eigenvalues and eigenvectors, right? So A is your sinc function. Is this a positive definite matrix, sinc?
Yes.
Because we studied autocorrelation function, right? Sinc corresponds to a colored spectrum. So this is a positive definite matrix. So now you can put everything together. So all its eigenvalues will be positive. In fact, what is lambda physically? So let's take this and let's plug it in here. Where was it? So this we had written as integral phi t f star of t dt. And we said when these two quantities are equal, I took it out, right? So this is going to be less than or equal to integral phi squared integral f squared, right? Integral f squared is 1. And integral phi squared is and integral phi squared is here. Phi is proportional to, look here, phi is equal to lambda ft. You need to have that equality, right? So if you want equality here, look at here, if you want equality here, this phi is going to be lambda multiplied by ft. So let me plug it in. Again, integral under f squared is 1. So you will see that this is your lambda. So you want to maximize this, right? So if you go through all this, the maximum value is going to be whatever is the largest eigenvalue of that system. So that all the eigenvalues are positive. That's good. Otherwise we would be in big trouble because energy will turn out to be negative and so on. Because we know this is a positive definite function, this is called the kernel. So these entries here. So I'm saying you discretize this. If you want to solve this, you can rewrite this integral. So you take the b naught t, that's your, so you discretize it. And then for both t and tau, then this will be, so this you replace by some I delta, this you replace by j delta, then this will be aij, is going to be sinc of I minus j delta, right? And all the sinc, when t equal to j, sinc is 1, so all the diagonal entries are 1. So you have this, you can go home and solve it and plot the eigenvalues. This is the theorem. The eigenvector corresponding to the largest eigenvalue is what you are looking for, because you are looking for this f. So this is the eigenvector associated with largest eigenvalue of this integral equation, integral 0 to b naught t sinc t minus tau f tau d tau equal to lambda ft. So you need to solve that either continuous domain or in the discrete domain, and that will answer this question. So we answered this optimization problem. I mean, you can generalize this problem. Now you can say what is the next best pulse and so on.